Okay, in our second half here, we are going to go through a couple of research summaries to practice what I've been talking about in the last section. So here's the first research summary. Carbon monoxide gas, CO, is toxic in air at concentrations above 0.1% by volume. Cars are the major source of atmospheric carbon monoxide in urban areas. Higher carbon monoxide levels are recorded during colder weather. A group of students proposed that cars emit more CO in colder air temperatures than in warmer temperatures during the first 15 minutes after they are started. The students do the following experiments to test the hypothesis. So the students have, the question is, why are carbon monoxide levels higher in colder weather? And the students have decided that the hypothesis they're going to propose is that cars emit more carbon monoxide in cold weather as opposed to warmer weather during their first 15 minutes. In other words, in the time it takes the car to warm up, starting from a cold temperature, it produces more carbon monoxide than if it were started in warm weather. So here are their experiments. Here is the first experiment. A student connected a hose to the tailpipe of a car. This student started the engine and collected the exhaust from the tailpipe in a plastic bag. The student then took a 1 milliliter sample from the bag with a syringe and injected the sample into a gas chromatograph. A gas chromatograph is a instrument that measures gas composition and shows percentages of various gases that are in the sample. The group then compared the exhaust of known mixtures of CO concentrations to determine the percentage by volume of carbon monoxide. Students took collections every 2 minutes through the first 15 minutes. They also took exhaust samples from 4 different cars at a temperature of minus 9 degrees centigrade. And here is the data that they collected. Now, although it was not outlined in their hypothesis or in their proposal, they took 2 different years of cars and 2 different models. So they had Model X from year 1978 and 1996 and Model Y from year 1978 and 1996. This happens many times in these types of experiments, as people will decide to do a couple other things, and indeed it's probably a little bit off from the directions I gave you before, that you should only look at one variable at a time. But be that as it may, they're looking at different models and different years, as well as the time over which the collections or the engines are sampled. And if you look at this data, remembering what we learned last week, it starts out, it goes up a little bit in the first 5 minutes, and then it drops off. It goes up in the first 5 to 7 minutes, then it drops off. Comparing these two, which are the same year but different model, this model clearly has more carbon monoxide than this model. Now, if you go to the different year, you get the same trend. It goes up a little bit and then drops, goes up a little bit and then drops. You also get the trend this way, in that Model Y is not quite as good as Model X. But if you look at the year comparison, it's clear that the later model cars are better in terms of carbon monoxide emissions. Now, they did the same 4 cars and tested at a different temperature, which was actually the original hypothesis was, does the temperature make a difference? And here are the results, and you see the same trends that we saw before. Flashing back just for a second, you can see that this column of numbers is generally higher than this column of numbers. The difference being the temperature here is warmer. The same is true of this column, and this column. You can see that this column of numbers is generally higher than this column, and so forth. And so those are the sorts of trends that you've noticed. So now let's take a look at a couple of questions. Do the results of experiment 1 support the hypothesis that at a given temperature, the time the exhaust of newer cars contains the lower percentages than older cars? Now, that wasn't the original hypothesis the students had. This is a different hypothesis that they're proposing now in this question. If the students had the hypothesis that newer model cars would do better than older model cars, then does the data support that? And as we went through this, you remember that indeed that was the case, that yes, the newer model cars had lower exhaust percentage. The newer model cars had a lower exhaust percentage than the older model cars. Now this top one says yes, but it specifies Model Y, and that's doesn't make any sense because both cars in the year have to be consistent with that in order to confirm the hypothesis. And then both no answers obviously are incorrect, regardless of what the verbiage is. A student thought that carbon dioxide in car exhaust may interfere with carbon monoxide detection. Now, this is one of those things that the last slide I showed you, which was, how do you deal with problems with the experiment? So it says, which procedure could he do to investigate this problem? Could he fill the bags with carbon dioxide before collecting the exhaust? Could he collect exhaust from additional cars? Could he inject a sample of air into the gas chromatograph? And then lastly, could he test a sample with known amounts of CO and CO2? Now the only answer here that makes sense is the last one. In other words, in order to see if his experimental results make sense, is to inject what's called a blank or a test sample that you know the answer to see how it compares with your ones that you don't know. And it is extremely common when you use instruments to do this in order to validate the results of your unknowns. And so the answer here is the bottom. Testing a sample with a known amount of CO and CO2 is the way to go. In experiment 1, which of the factors was the independent variable? The method of sample collection, the volume of exhaust collected, the model of the car detected, the year of the car tested, the temperature at which the engine was started. Well, in experiment 1, the temperature was constant. The model of car tested was the same in two groups. When you looked at the data varied based on the year of the car. The first two doesn't make any sense because in the methods section they told you that the volume of exhaust and the sample collection was the same. The temperature was the same. And so the comparison was not made between models but between years. And so the answer is the year of the cars tested. Many states require annual testing of cars to determine the level of their carbon monoxide emissions. To determine the maximum percentage of CO, when is the best time after starting the engine to check the exhaust? If you look back at the tables, and I'm not going to go back there, but if you look back at the tables, you'll see the answer to this is 5 to 7 minutes. The point at which all of the cars seem to have their highest carbon monoxide emission is around 5 to 7 minutes after starting. And this was true at both temperatures. How would the results be affected, if at all, if the syringe content were contaminated with carbon monoxide free air? That is, if the syringe accidentally sucked in a little extra air that had no carbon monoxide in it. The measured percentages of carbon monoxide in the exhaust, how would they be affected? Well, if you think about it, if you add extra air that has no carbon monoxide in it, the denominator, which is the volume, total volume, would increase, but the amount of carbon monoxide would stay the same. So at all temperatures, at all testing, the percentages would be lower than the actual percentages. And so that's the answer. The percentages are lower than the actual percentages. The second research summary we'll review is the following. Solids, liquids, and gases usually expand when heated. Scientists conducted 3 experiments to study the expansion of different substances. In the first experiment, scientists used linear expansion of wire to measure the expansion of different metals. So their hypothesis here is that different metals will have a different level of expansion, or a different amount of expansion. In each trial, a wire was connected to a voltage source and then run through a series of pulleys attached to a weight. The temperature was varied in a controlled fashion by varying the voltage in the wire. The amount of expansion was directly proportional to the rotation of the final pulley. And this top diagram is how this was set up. And what you see here is this is the final pulley. And so when you heat the wire, there's a weight here, it pulls down. If the wire expands, it pulls down this way, and the scale moves this way down toward the ground. So the weight causes the scale to move down. So when you start at a certain temperature here, when it heats up, if it expands, it's going to move in this direction. And then the second diagram here shows the various outcomes, the amount of expansion at each temperature, and different metal types. And what you see is that the least expansion is with nickel, and the greatest expansion is with aluminum. Just reading this table, at 80 degrees, the linear expansion of aluminum is about 20.2 millimeters. Brass is a little less than 0.15 millimeters. Iron is a little less than 0.1 millimeters, and nickel is about 0.05 millimeters. The second experiment, scientists placed a sample of liquid in a stopper test tube filled with a graduated capillary tube, and the test tube was then placed in a temperature-controlled water bath. So the sample is put in a tube like this. The water bath can be warmed, and then the expansion can be measured in the capillary tube. You see the data results, the various temperatures, and the rise of liquid in the tube in millimeters, water, glycerin, and ethanol. And obviously ethanol expands the most, water expands the least. The third experiment, scientists placed 20 milliliters of gas in a glass syringe at room temperature in a temperature-controlled water bath. They measured the change in the gas volume for 3 gases as they increased the temperature. Here is the design, and as you increase the temperature, the stopper will go up, or the plunger will go up, noting the increase in volume. And here's the data, and as it turns out, all 3 of these gases expanded about the same over that temperature range. Here are the questions. In experiment 2, which of the following temperatures did all the liquids have the same volume? So if we go back, all the liquids had the same volume at 20 degrees centigrade. So the answer is 20 degrees centigrade. A scientist has hypothesized that the temperature of gas increases when the volume should increase at a constant pressure. So if you increase the temperature, the volume should increase. Does the experiment 3 support this hypothesis? I'm not going to go back there, but if you look, the answer is yes, because the graph shows a steady increase, a linear increase in volume as the temperature increases, and this is true for all 3 gases. So the answer is this first one. Yes, the volume of all 3 gases tested increased as the temperature increased. Based on experiment 1, if an engineer needed a metal that resisted stretching under the heat and tension, which of the following would be best? You remember, if you look back at the bottom line, the one that expanded the least was nickel. And if you don't remember that, you can click back to that point in the slides and look at it. Based on experiment 3, if a researcher fills a balloon with air at room temperature and places it on the surface of a heated water bath, as the temperature of the water increases, the volume of the balloon would do what? It would increase. It would not decrease at any time because, as we said in the previous question, two questions ago, you showed with the consistent upward increase, and it didn't really matter which gas was in there, that the volume would increase. And then lastly, a scientist tested a copper wire in the experimental design 1. At 80 degrees, the linear expansion was 0.12. Which of the following lists arranged the wire from the shortest to the longest? Okay, if we go back and look at this, if we start, nickel would be the shortest because it would only expand 0.05. Then iron, 0.1. Then the copper would fit next at 0.12. Then brass at 0.15. And then lastly aluminum. So now all we have to do is go back and find the answer that is nickel, iron, copper, brass, and aluminum. And there it is. Nickel, iron, copper, brass, and aluminum.